All right, so to continue our series of induction and the different types, we're going to have a look at matrices next and how to use inductive arguments to prove matrix equations. Just beforehand, I do want to just remind our last video was the complex series. So I'm just going to give you one here. So prove that this complex series here is equal to this. I'd like you to freeze now and have a go yourself, because you can sit here listening to me all day, but unless you have a go, you're going to struggle to be able to do it. So if you could have a go at that, that'd be great to prove that. If you have any troubles, you can ask me a question, but that's just another good one as well. But let's get into matrices, because that's why we're all here. All right, so for this matrix, I've been asked to prove that this 2 by 2, 1, 1, 0, 1 to the power of n is equal to 1, n, 0, 1. Okay, might make sense, might look obvious to you, might not, which is fine. But let's prove it using induction. All right, so I just made myself a little bit more room here to do the induction. And we've got to prove it for all positive integers n, so positive. So this proof, again, we start these by the same thing, is going to be by the principle of mathematical induction, and you are going to write that out in full, like we discussed before. So we always start with the first one, number 1. If you have a go, if you want to have a go before me and just pause now and then catch up and see if you do it right, that's also probably a good idea. But for 1, if n equals 1, what we get is 1, 1, 0, 1 to the power of 1 equals 1, 1, 0, 1. Okay, that is a 0. So we know that anything to the power of 1 is just itself, so it's going to be 1, 1, 0, 1, which equals this, which is true. So therefore, P of 1 is true. Okay, so we've done P of 1. So the next thing we have to do is have a look at P of k, P of k plus 1. So let's do that now. So always start with our little 2. If P of k is true, then 1, 1, 0, 1 to the power of k equals 1, k, 0, 1. All right, so that's cool, and that's going to be really handy later on. But let's just leave it for now. But now, so we always write P of k out, and we don't really do anything from there. We know we come back and nab some stuff from there. Now, for P of k plus 1, what we get is 1, 1, 0, 1 to the power of k plus 1 equals 1, k plus 1, 0, 1. All right, now we've got something interesting. So what I'm going to do is I'm going to expand this side here, this left-hand side. All right, because we can't really do anything to the right-hand side. It's kind of just happy being there. So I'm going to go to this left-hand side here. So the left-hand side, you don't have to write this, but I feel like it's good to keep track of what you're doing. So left-hand side, you get 1, 1, 0, 1. We know if we've got something like a to the power of x plus 1, we could split that up into a to the power of x times by a to the power of 1. All right, that's the same thing. So we're going to do that here. So a to the power of k plus 1 could be split into our matrix to the power of k times by our matrix to the power of 1. All right, so that's our first step, splitting it up like that. So again, this is the part that comes up every time, the inductive step, that we realize that for our left-hand side, we get this thing here that we can't really do anything else, but we look at it and we say, all right, I've seen this before, right here. and it was equal to this thing, which is something I could probably deal with. Yeah. So let's have a go at that. I've got to apologize as well, and hopefully you did catch me. This is supposed to be a 1. 1. All right, because that wouldn't have worked if I didn't do it. So what we're doing now is we're substituting this green in for this other green. So I can write that equals 1K01 times by 1101. All right, and I multiply using my matrix multiplication techniques, which is first row times the first column. All right, and that gives me my first number. So that's going to be back to black. So 1 times 1 is 1, plus k times 0 is 0. The next one is going to be my first row times by my second column. It's going to give me my first row, second column over here. So 1 times 1 is 1, plus k times 1 is k. Then I'm going to do my bottom row. So my bottom row times by my first one is going to give me bottom first. 0 times 1 is 0. 1 times 0 is 0. And my bottom row again times my second column is going to give me 0 times 1 is 0, plus 1 times 1 is 1. So if I just work this out, 0 plus 1 is 1, 1 plus k, 0, 1. I get this. So what we get is, we might recognize this. This here is equal to this. I know I've got my k and my 1 the other way around, but k plus 1, 1 plus k, they're the same thing. So we've proven that that's true, k plus 1. And we need to write that down formally again. So again, pretty standard. So therefore, p of k plus 1 is also true. So since p of 1 is true, and p of k plus 1 is true wherever p of k is true, then p of n is true for all. Remember that sneaky for all. All right, but you can write for all n belonging to the real positive integers. Okay, just have to sum it up by writing that was because of the principle of mathematical induction. Okay, so same again. Maybe this one's a little bit quicker, but same process, just matrices in between the sandwich of formality that induction brings. Okay, thank you.